I'm going to talk about extracting point and patch type features from images. So we would want to find distinctive points or patches in images so that we can, for example, recognize objects or track these features from one image to the next. We would want to find these small patches that are locally unique. So good types of features would be bright dots or corners. Or bad types of features would be regions in with constant values, such as in the background here, or long straight edges along here, because those would be difficult to find the corresponding matches in another image. So in this, we're going to look at first the Moravec interest operator. It's an old operator that is no longer used, but I thought it would be helpful to understand some of the concepts. And then we'll move on to ones that are currently used, which is the KLT corner detector and the SIFT feature detector. So the Moravec interest operator relies on looking at each point in four directions: horizontal, vertical, and the two diagonal directions. So at each point, it's going to try to find, it's going to evaluate the variance of the intensities along that particular axis. So it's going to compute the variance in the horizontal pixels. That would range from x minus w to x plus w. The variance in the vertical dimension, which would be y minus w to y plus w, and also along the two diagonal directions. And then once it finds those four variances at each point, it takes the minimum of the four variances, and that is the interest value operator at that point. So an example would, in a case of a uniform region, the operator, of course, would be low because the variance would be 0. If we take the operator in the vicinity of a vertical or horizontal step edge, say I take the value right here at that pixel, the variance in the horizontal direction, let's say if I have n points that way, would be 1 over the sum of the value, let's call it x sub I minus mu squared. And mu, of course, is 0.5 in this particular direction, because half the pixels are 0 and half the pixels are 1. So this would come out to be 1 over n, let's say n over 2 times minus 0.5 plus 1 over n over 2 plus 0.5 squared. So that would come out to be just 0.5 squared, which is 0.25. So the horizontal variance would be 0.25. The diagonal variance would also be 0.25. But the vertical variance, this one right here, whoops, let me just change that. Let me just look at that vertical variance. So if I'm centered at this pixel here and the white, the vertical variance is 0. So that means if I take the minimum of all four of those variances, it would be 0. So that's good, because I don't like this pixel anyway, because it's not very localizable along that direction. In contrast, at a corner like this, the score is high. So I have a high variance horizontally, a high variance vertically, and also in the two diagonal directions. So the Moravec operator would find a corner and signal that as a strong, interesting point. This is the result of running a Moravec interest operator on this image. I'll describe in a minute here how this is done, but I wanted to show you the results. It does tend to pick up corners like you see, or distinctive features such as this the screw and nothing in the background. However, it does tend to also pick up some features that we wouldn't want along these long straight edges. So in Matlab, we can implement the Moravec operator fairly efficiently. So let's look at the definition of a variance. So a variance is defined by this equation here. We take the sum of the squares of the values minus the mean. Spreading or breaking that out into more detail, I can compute the quantity in the square, and then pass the summation through those terms. So I can see that this term evaluates to just mu squared. This term is the mean, so it's 2 mu times mu. And so we get this result, minus 2 mu squared plus mu squared is just minus mu squared. So what we have here is a fairly easy way to compute the result. So instead of first going through and finding mu and then scanning through the values a second time to compute the variance, we can do it all at once by computing the sum of the squares and the sum of the values themselves, the sum of the x sub i's as shown here. So the approach would be to compute the mean of each local window at each point, that's the mu, compute the square of each point, the x squares, and the sum, the local sum at each point, and then combine those to get the variance using this equation here. So in Matlab, let's show how to do this. So we would set up a filter, a 1 by n filter composed of ones. Let's call that HH. And we would evolve or correlate that with the image, and the result would be to sum all the values in that filter and divide by n. So that would give us an image of means where each point represents the mean of a horizontal window centered at that point. We would then take the image and square each pixel to produce an image of squared pixels, and apply this filter again to that to compute the sum of the squares at each point. And then finally compute the variance by subtracting the means squared divided by the square of the means. So we do the same thing for the other directions to get a variance in the horizontal, variance in the vertical, and the two diagonals, and then take the minimum to compute an image of interest point values at each pixel. So this is the Matlab program for the entire thing. So here you can see we're setting up that filter that's 1 by n. The diagonal filter is set up by this Matlab function called I, which is a identity matrix. So it's a diagonal matrix of ones down the diagonal. And then this flip left-right just computes the diagonal in the other direction. So these lines compute the means in those various directions, and these lines compute the mean of the squares. And then these compute the variance by subtracting the mean of the squares minus the square of the means. And finally, we take the minimum of those results pair by pair. The min only takes two elements as the input. So I first take the minimum of each pixel between the horizontal and vertical variance images, and the two diagonals, and then the min of those two. So this is the result of running that program. These are the four separate variances in the horizontal, vertical, diagonal, and the other diagonal. So then pixel by pixel we take the minimum of these four values, and we get this image. So you can see that it does seem to pick up corners nicely, and distinctive points like this, but we still need to extract individual points now from this image instead of an entire image of scores. So we'll talk about that in a little bit. But just before we leave this, the problem with this operator is when you deal with a step edge, for example, that is not a vertical edge or a horizontal edge or a 45-degree angle edge. So imagine that I tried to compute the variance at this point. I would get a high variance vertically, a high variance horizontally, and I'd also get a high variance in the two 45-degree angle directions. So these four directions at 45 degrees are not aligned with the step edge that I have. So I would signal a good step edge even along a long straight edge like this, which would not be a good thing.